factors. So this is unfortunate. So I just go back and say everything that I said again, because otherwise some recording will be missing. So I try to be a little bit faster so that we are not losing too much time. So please always make me aware should I forget to press the record button if you see it. So today we would like to start a new chapter, which is about silicates. So silicates are worthy to well, be uncovered because they are the most abundant class of compounds in the Earth's crust. Okay, so this is mainly due to the fact that the oxygen and the silicon are the two most abundant elements. So we have 60.4 weight% of oxygen in the Earth's crust and 20.5% of silicon in the Earth's crust. So most of that oxygen is actually not bound in the atmosphere, it's not in the atmosphere or in the water, it's actually bound as silicates within the solid part of the Earth's crust. So the third most abundant element is aluminum. So aluminum and silicon have similar chemical properties, and many silicates are actually alumosilicates. Okay, so that boosts the silicate content in the Earth's crust further. So the next most abundant element is then hydrogen with 2.9 weight%. So we should consider here that hydrogen is significantly lighter than all the other elements because it has only one proton. If we wanted to compare the abundance of hydrogen with oxygen on a molar basis, we would have to take that percentage by 16 because oxygen is 16 times heavier than proton, but still oxygen would remain to be the most abundant element also on a molar basis. So the other relatively abundant elements are sodium with 2.6%, then calcium, iron, magnesium, and potassium. All these 9 elements together make up for 99.5% of the Earth's crust. So all other elements make up for less than 0.5%. So overall, 95% of all minerals in the Earth's crust are silicate based. So the abundance of silicates in the Earth's crust is one important reason to study them. We are virtually surrounded by silicates every day, and we are virtually walking on silicates every day. So here are the most important minerals overall. Most of them are silicates. So the most abundant mineral is plagioclase. It's sodium, aluminum, silicon oxide, and a calcium alumosilicate. So the next most abundant one is feldspar, which is potassium alumosilicate. Then we have quartz, which is the parent compound of all silicates, which has the composition SiO2. And then we have next the so-called amphiboles, which are a band silicate, pyroxene, which is a chain silicate, biotite, which is a phyllosilicate, and we will talk about these terms shortly in more detail. So the most abundant mineral, which is not a silicate, is magnetite and ilmenite. So magnetite is Fe3O4 and ilmenite is an iron titanate, FeTiO3. So the abundance of silicates is one important reason to study them. Another one is their structural diversity. So overall, more than 1,000 different silicate structure types are known. So in order to understand that structural diversity, it's worthy to look at the structural principles in silicates. So nearly all silicates are made of SiO4 tetrahedra as primary building units, whereby the oxygens can either be bridging, bound to two silicons, or they can be terminal, being bound only to one silicon. So for the terminal oxygen, we have a negative charge at the oxygen atom, and that negative charge then needs to be charge compensated by a cation in the silicate. So overall, the silicon to oxygen ratio in silicates can vary between 0.5 in silicon dioxide and 0.25 in the orthosilicate SiO4 4-, but of course you can have everything in between. So there are many possibilities for combinations of terminal and bridging oxygens. So another important factor to consider is that the silicon-oxygen-silicon bond angle can vary a lot. It can vary between about 109 degrees, which is the ideal tetrahedral angle, and 180 degrees. The average bond angle is about 140 degrees. So this is significantly larger than the tetrahedral bond angle. And the explanation for that is that the silicon oxygen bonds have partial double bond character. And you can see this when you look at the silicon oxygen bond length. So a typical silicon oxygen bond length is 162 picometer. This can be measured by X-ray diffraction. However, the sum of the covalent radii is significantly longer. So you all probably know that bond length relates to bond order. So the fact that we have a bond length which is typically smaller than the sum of the covalent radii indicates that we do not have simple single bonds, but often the bonds have double bond character. In other words, the formal electron lone pairs that are here at the oxygen are partially involved in the bonding, whereby the degree of involvement depends on the individual silicate. So that makes this bond angle here very variable, and that allows for the structural diversity in silicates, because there are more ways possible as structures can be realized. Okay, so most but not all silicates have an SiO4 tetrahedra as the primary building unit. One exception is Stishovite, which is a high pressure polymorph of silica. Okay, so in Stishovite we have SiO6 octahedra. So the coordination number of silicon is 6. The coordination number of oxygen is 3. The Stishovite makes a structure we actually know. It makes a so-called rutile structure. Remember, rutile has is a hexagonal close-packed structure of spheres, in this case oxygen, whereby 50% of the octahedral holes are occupied in a isotropic fashion. The unit cell is distorted from hexagonal to tetragonal. So why does Stishovite have higher coordination numbers for silicon oxygen? It's because it's a high pressure polymorph, so exists actually only above pressures of 12 gigapascals. And high pressure tends to favor denser phases, okay? And denser phases are typically phases in which the atoms have a higher coordination number, because then they can become more closely packed. Okay, this is called the pressure coordination rule. So higher pressure tends to come along with higher coordination numbers. Interestingly, in the Stishovite, the bond length is increased in comparison to SiO2 polymorphs in which we have SiO4 tetrahedra. So this is known as the pressure distance paradox. However, it's not really a paradox when you consider that the coordination number has increased in Stishovite in comparison to other forms of SiO2. So overall, we still have a denser phase despite the higher bond length, just because the coordination number increases. So Stishovite has also interesting properties. It's actually the hardest oxide known. It is thermodynamically stable only above about 10-12 gigapascals at ambient temperature, but it's actually metastable at atmospheric pressure up to about 500 degrees Celsius. You can make it at very high pressure, and then you can release the pressure, and the Stishovite, due to its strong bonding within them, remains metastable. Only when you heat it to a higher temperature, then it slowly transforms back into an ambient pressure polymorph. Okay, so now we have learned that silicates show a great structural diversity. We have many different structures, silicate structures. The question is, how can we classify them? And scientists have thought about this already since pretty early on. So the first systematic classification was done by Bragg, which was then further extended by Friedrich Liebau, who has written an important book about silicate chemistry, which is still kind of a standard in silicate chemistry, structural chemistry of silicates, structure, bonding, and classification. So according to Liebau, we can classify silicates according to the following principles. So we first look at the coordination number of silicon, which is almost always 4, as we said. Then we look at the so-called linkedness, R, the connectedness, C, the branchedness, BR, the dimensionality, D, the multiplicity, M, and the periodicity, P. So let us now systematically go through all these parameters. So we already discussed the coordination number. Let us directly move over to the linkedness. So the linkedness tells you how many corners are being shared between two SiO4 tetrahedra. So when we have only isolated SiO4 tetrahedra and there's no other tetrahedron attached, well, of course, the linkedness L is equal to 0. When we have corner sharing tetrahedra, then, well, sorry, one corner is being shared and the linkedness is 1. When two corners are being shared, then actually an edge is shared and then the linkedness is 2. And when 3 corners are being shared, as shown here, and that means that a face is shared, then L is equal to 3. So in practice, only L equal to 0 and L equal to 1 is realized in silicates. So silicates never edge share and they also never face share. The reason for that is the relatively high ionicity in silicates. So because of that, the centers of the tetrahedra where the silicon resides are highly positively charged. And of course, these positive charges repel each other. Okay, so for that reason, these silicon atoms try to adopt the greatest possible distance to each other. And the greatest possible distance can be achieved in corner sharing tetrahedra. Okay, in edge sharing and in face sharing tetrahedra, the two silicon centers would come too close together to be stable. Okay, therefore silicates always prepare corner sharing over edge sharing and face sharing. So next, let us look at the connectedness in silicates. So connectedness means by how many other tetrahedra, specific tetrahedra we look at is connected to. Okay, so the connectedness is expressed by the capital letter C. So when the connectedness is 0, then that means that we have isolated SiO4 tetrahedra. We have SiO4 4 minus anions. Okay, so when the connectedness is 1, then that means that a particular tetrahedron is connected via a corner to one other tetrahedron, okay, but no more than that. When the connectedness is 2, then that means that one particular tetrahedron that we look at is connected to 2 other tetrahedra. So when the connectedness is 3, then that means that the tetrahedron that we look at is connected to 3 other tetrahedra. And when the connectedness is 4, then that means that the tetrahedron that we look at is connected to 4 other tetrahedra. So we can call these silicons, which are in the center of these tetrahedra, also Q sites. So when C is equal to 0, then we mean that we have a Q0 site and we have an isolated tetrahedron. When we have a Q1 site, that's also called a primary Si, then the connectedness is 1. When we have a Q2 site, then the connectedness is 2. We have a secondary Si. When we have a Q3 site, then we have a tertiary Si. Okay. And when we have a Q4 site, then we have a quaternary Si. Okay, so now let's move on from the connectedness in silicates to the branchedness in silicates. So in the most simple case, the SiO4 tetrahedra are linked together in an unbranched way. So they make either unbranched chains or unbranched rings. Okay, so you see here a few examples of that. So here we have just 2 SiO4 tetrahedra linked together in an unbranched way. So here we have 3, and here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we could also make an infinite chains of tetrahedra which are all unbranched, or we can close these chains to form rings. You see one example here. Here we have an example of a ring which has 4 members of tetrahedra. Okay. So now, however, these chains and rings can also be branched, and one type of branchedness is the open branchedness. Okay, and that means that we have terminal side chains attached to a main chain. So in the most simple case, that a terminal side chain can consist only of 1 tetrahedron. So see here 2 examples. So we here have a main chain of 3 tetrahedra with 2 side chains. Okay. So here we have a ring as the main chain and 2 tetrahedra as the side chains. So here we have another example of an open branch silicates. So in this case, we have, again, a ring as the main chain, and now side chains that are comprised of 2 tetrahedra. Okay, so here in the last example, we have again a main chain, which is now a chain of 1, 2, 3, 4, 5, 6, 7, 8 tetrahedra. We have again side chains made of 1 tetrahedron. So now in addition to that, you can also have loop branching, and then the side chain closes to form a loop. So you see here one example. So in this case, we define this chain here to be the main chain. And then we have these 2 tetrahedra to make the side chain, but now the side chains are not terminal. They actually make a closed loop. And for these 2 tetrahedra here, we are also making a closed loop. So last but not least, we can also have what is called an open loop branchedness, abbreviated OLB. And so in this case, we have both terminal side chains and side chains that form a loop. You see here an example. So these red tetrahedra here, they again make the main chain. And now these tetrahedra here, they are an open branch, and these tetrahedra here and here, they make the loop branch. So these are the type of branchednesses that you can have in silicates. All right, now let's go further to dimensionality. So essentially, we distinguish between 0-dimensional silicates, 1-dimensional silicates, 2-dimensional silicates, and 3-dimensional silicates. So 0-dimensional silicates with D equal to 0 are either neso, soro, or ring silicates. So in the most simple case, we have a so-called nesosilicate, okay, where we have only a single SiO4 4- anion, which is not interconnected to any other SiO4 tetrahedra. Okay, so when we have a source silicate, then we have a finite number, usually a few, SiO4 tetrahedra linked together. So you see here an Si2O76 minus anion made of 2 corner sharing SiO4 tetrahedra. It is actually useful to understand how you can derive the structure of a silicate from its formula. Okay, so for instance, when you have a formula in which you have a silicate in which you have the ratio of silicon to oxygen is 1 to 4, then you know that this actually must be a nesosilicate. Okay, and that silicate must have 4- charge. Okay, and that becomes clear from the fact that each oxygen is terminal here. So each oxygen must have a 1- charge, and that gives overall a 4- negative charge. So here the formula is Si2O76 minus. Why is it so? Well, we certainly have 2 silicons. So now we have 7 oxygens, okay, whereby 6 of these oxygens are terminal. These are these ones here, and these ones here, and 1 is bridging. So the bridging one doesn't carry a charge. but the 6 terminal ones carry a charge. Okay, therefore we have an Si2O76 minus. Therefore, when you see a formula of a silicate that contains the unit Si2O7, you might actually suspect directly that this may be a source silicate in which 2 SiO4 units are linked together via a shared corner. Okay, so then we have the possibility to make rings. When we make rings, then we also have a 0-dimensional silicate because our silicate is not extended in any dimension. So you see here 2 examples. So here you have a 3-ring and you have a 6-membered ring. So ring silicates ring silicate anions have the composition SiO3 2 minus, okay, whereby that stoichiometry is then multiplied with the number of ring members. Okay, so when we have a 3-ring, we have SiO3 2 minus 3. When we have a 6-membered ring, then we have the composition SiO3 2 minus 6. Okay, so when the stoichiometric ratio of silicon to oxygen in your silicate is 1:3, you may suspect that this may be a ring silicate. Okay, so why do we have that stoichiometry and why do we have a 2 negative charge? Okay, we can easily derive this when we consider that in a ring silicate, each SiO4 tetrahedron has 2 shared oxygens and 2 terminal oxygens. Okay, so the terminal oxygens carry the 2 negative charges. Okay, so now each oxygen here is being shared. Therefore, it counts only a half to the formula unit, while the 2 terminal oxygens count fully to the formula unit. So per tetrahedron, you therefore have SiO2, okay, plus another O, because these 2 O's are being shared. Okay, and that gives overall SiO3, and we have a 2 minus charge because the oxygen, these 2 terminal oxygens carry a 2 minus negative charge. Okay, this is of course also true for rings that have a different number of members. Okay, also in this 6-ring, for example, we have only tetrahedra in which 2 oxygens are being shared, counting a half, 2 oxygens are being terminal, counting fully, okay, and carrying the 2 negative charges. Okay, so in all these silicates, we do not have extended structures. Therefore, these silicates have the dimensionality 0. So now let's move over from yes, Tom.
Yeah, I was just curious if there is a maximum size. You know, you have 6 there, but at some point it's got to be unfavorable stability-wise, right? Or...
That's right. So certainly some ring sizes are more common than other ring sizes. And 3-membered rings and 6-membered rings are pretty common. Very large rings then become quite uncommon. So we will talk about which examples of silicates are realized more often and which examples of silicates are realized less often, and for what reasons somewhat later. So much has to do with ring strain in the case of ring silicates, another important parameter is the repulsion of formal charges. I will talk about this in more detail actually in the next lecture, but it's a good comment. So not all ring sizes are equally often realized in nature because of different thermodynamic stability, part of which is due to ring strength. But 3-membered rings and 6-membered rings are pretty common. Also 4-membered rings are relatively common. 8-membered rings are still fairly common, but I'm not aware of a ring silicate in which we have, let's say, 20 members. So that becomes exceedingly rare.
Okay, thank you.
Okay. So now let's move over from zero-dimensional silicates to one-dimensional silicates. So one-dimensional silicates are either inosilicates or band silicates. So in an inosilicate, you have single infinite chains of SiO4 tetrahedra, which are corner sharing. Okay, so now the dimensionality of this inosilicate is 1 because you have an infinite structure in one dimension. Okay, so the composition of an inosilicate, anion, is also SiO3 2 minus. Okay, the empirical formula. That's again because these chains are made of SiO4 tetrahedra, all of which have 2 oxygens which are shared between 2 silicon atoms and 2 oxygens which are terminal, whereby these terminal ones again carry the negative charges, okay, that you see here in the formula. Okay, so a silicate that has the composition SiO3 2 minus, whereby of course the negative charges then have to be charge compensated by a cation, for instance, sodium, calcium, or whatever, then you may actually suspect this may also be an inosilicate, okay, or a ring silicate. All right, then you can actually link single chains together to make band silicates. Yeah, as shown here. So here you have a band silicate which is made of, well, 2 chains fused together. Again, we have an extended structure only in 1 dimension, therefore this is still just a 1-dimensional silicate. So what's the composition? So in this case, the composition is Si4O11 6 minus. Okay. Now we can understand this again when we look at the individual tetrahedra, whereby we have to realize now that there are 2 different tetrahedra in this band. Okay. So one type of tetrahedron is this one here, which has 2 terminal oxygens, which carry a 1 minus charge each, and 2 oxygens, which are shared. However, now in addition to that, you have these kinds of tetrahedra, and you see that for these kinds of tetrahedra, 3 oxygens are being shared, okay, and 1 oxygen is being terminal. Okay, so now what does that give? And we can actually maybe briefly calculate this. So I just write this down here. So for the first tetrahedron, we have, well, SiO2, okay, whereby that's 2 fully counts, okay, and then O, another O for these 2 oxygens which are being shared, okay. So they only count a half, therefore they only contribute 1. So I don't know how to produce a subscript here, so please forgive me that. Maybe I can just do it the regular way. No, that doesn't work. So, oh, okay, so then that is 2 minus, okay. Well, that's 2 minus. Okay, and then in addition, we have the other tetrahedron, this one here, which is Si, whereby now we have this this one here, fully counting, yeah, SiO, and now the other three only count 0.5. So 3 times 0.5, that gives 1.5. SiO, let's say 1, O, 1.5. Okay, now what's the charge here at this tetrahedron? Well, that only has a 1 minus charge. Okay, so that is equal to, well, Si2 O, and now we can just add the oxygens together. So that here gives 3. So this one gives 4. Okay, and 4 plus 1.5, well, that gives 5 plus 5.5. O, 5.5. Now, what is the charge? Well, we have 1 minus here and 3 minus here. Okay, so that gives overall 3 minus. Okay, and that well, now has a non-integer number of oxygens, so we can just multiply that formula unit by 2, and then this becomes Si4O11 6 minus. Okay, and that's the same that you actually see here. Okay, so again, you can actually correlate well, empirical formula with a structure. Or so the empirical formula gives you a clue what the structure may be. All right, so now last but not least, let's go to the two-dimensional silicates. Now in two-dimensional silicate, you have an extended silicate structure in 2 dimensions. Okay, so this is shown here in an example. Now we can again ask, well, what's the chemical composition? And again, we can answer this question by looking at the individual tetrahedra. So we see now that each and every tetrahedron has 3 bridging oxygen and 1 terminal oxygen. Okay, so for this case, maybe I just start here a new line. We have SiO for the one that has the negative charge, plus the 3 that are being shared. They only count a half, so 3 times a half, that is 1.5. Okay, O1, O 1.5. Okay. So now, what is the charge? Can anybody tell me the charge? So the charge is determined by this one terminal oxygen here. Only that terminal oxygen carries a charge, so we have 1 minus. Yeah. So again, we have here a non-integer number. So we just multiply that formula unit by 2. So this is Si sorry, Si2O5, if we multiply this by 2, and then we have 2 minus. Okay, so when you see a silicate where silicon to oxygen has a stoichiometric ratio of 2 to 5, you may actually suspect that this is a two-dimensional silicate. All right, so last but not least, we have also tectosilicates. So these are three-dimensional frameworks. So these three-dimensional frameworks arise when you now interconnect basically layers in the third dimensions, in 3 dimensions somehow. So most tectosilicates are aluminosilicates. So in most cases, actually, the SiO4 tetrahedra are linked by AlO4 tetrahedra. So you call this as tectosilicates, even though you have a different tetrahedral center here. Okay, so I see that we are already a little bit over the time. So let us stop